Good afternoon to everybody. But not only afternoon, I think that I should say also good evening and good morning, especially to our speakers from Brazil. So I'm happy to announce the talk by my friend Thiago de Melo, and his talk is Gottlieb Group of some more spaces. Thiago, you have a talk now.
Oh, thank you so much. First of all, I would like to thank the organizing committee for this opportunity to present this talk here. I would like to say a few words about this project. So, as Professor Marek introduced, I'm from Brazil, a small city near São Paulo city. I think São Paulo is a very famous city in Brazil. And I'll talk about the Gottlieb groups of summer spaces. And this is a joint work with Professor Marek and from Poland and Rodrigo from Brazil. So first is let's fix some notations and terminology. It's classical in topology to work with CW complexes. And so during this talk, all spaces are connected, based, and they have a homotopy type of CW complexes. Also, as usually, the maps are continuous maps and based, because we are going to talk about homotopy classes and so on. So because of this, we don't distinguish between a map and its homotopy class. And the classical notation for identity on a space X is the iota X, and also iota N for the identity map on the N-sphere SN. Also, we have the classical Hopf map, eta N, from sphere SN+1 to SN. So it's very common to see this map appearing in homotopy theory, especially eta 2, eta 3, and others. So this is the notation and terminology we need. So I'd like to say a little bit about the Gottlieb group. We work many times with homotopy groups. Since the beginning of the study, we know the fundamental group, and then we start to work with higher homotopy groups. But there are some subgroups of homotopy group that are very interesting to us. So what is a Gottlieb group of a space X? So we consider a path-connected space. And in this paper from 1965, Gottlieb introduced the Gottlieb group for m equal 1. So we say only g of x or g1 of x. And a few years later, in 1969, he defined for higher n. So we have the general Gottlieb group of a space X. And what is this group or subgroup? We consider all elements in the homotopy group such that they can be represented by a map from sphere to X in a way that the wedge with identity of X can be extended to the product. So if we have a map representing a class and we take the wedge with identity and this wedge can be extended to the Cartesian product, we say that this F belongs to the Gottlieb group of X. And of course, there are many properties. We can see that independent of the map you choose in the class, independent of the base point, and so on. But this is the subgroup, the Gottlieb group. So a useful tool we have here to compute some groups is this fact. We say that alpha belongs to Gottlieb group of sigma x. Sigma x is suspension of x. Alpha belongs to GM if and only if the Whitehead product with identity of sigma x is 0. And a similar argument, a similar tool is this following. We say that alpha belongs to Gottlieb of a wedge of two suspensions if and only if the Whitehead product with both inclusions are trivial. So we take J1 and J2, the two inclusions, and if the product with alpha is 0, alpha belongs to Gottlieb group. So we are we are working with Moore spaces. In this case, to us, X is a Moore space. So just to fix the terminology, a Moore space is a space with a homology concentrated in one dimension. So that is, we have abelian group A, and then the reduced homology of X is 0, except the any homology. And this one should be the group A from where we started. So this is a Moore space. And it is very interesting because if we have a finitely generated abelian group, we can decompose this Moore space using the free part of the group and the torsion part. And we have a wedge sum of spheres and other Moore spaces. So this is very useful to simplify some computations. So we can conclude from this paper from Gottlieb. We have this consequence. If we have Gn of the Moore space MAN, if n is even, this group is 0. So I would like to pay attention that we, in this case, we are working with Gn and the same n we use in the Moore space. So it's Gn MAN. If n is even, 0, or if n is odd and the rank of A is not 1. And about the rank 1, what we find here? Only for A equals Z, if n is 137 or odd but not 137. In this case, we have the 2 times Z or Z, depending these cases. But I pay attention in the rank. In this case, the rank is 1. Also, in addition, in this paper by Gottlieb and Maruyama, they go a little bit further. They take the group Z plus T, and T is a finite abelian group. And they show that if n is odd, Gn of this Moore space is infinity cyclic. But here again is Gn and the same n in the Moore space. So what is this, the outline of this work? In the same paper, Gottlieb Maruyama, they close the paper with this statement. It would be interesting to compute other Gottlieb groups of Moore spaces, such as Gn plus 1. So now we change the n by n plus 1. Also, we noticed that in this book, Golosinski and Mukai, they compute many groups for different A's, different Moore spaces. And we find there some results on Gn plus k of the Moore space. And especially for A having torsion subgroup with odd order. So the question is, what can we say if the order is even? So in the sequel, I will summarize some facts to work with groups where the torsion subgroup has order 2 mod 4. And then we can compute some Gottlieb groups Gn plus k. And k could be 1, 2, up to 5, for example. So the idea is to decompose the Gottlieb group of the wedge, and then we can use a fact that this group is contained in the image of both groups, Gk of the first Moore space and the second Moore space. So if we have 2 groups, A and B, we consider Moore spaces to each one, and the Gottlieb of the wedge is inside the image of each Gottlieb group. This is why I said that to simplify some computations, it is good to use wedge of Moore space. And then we can extend this to wedge of spheres, for example. If we have many spheres, if we take upper bound to capital N, the Gottlieb group of this wedge is 0. And the sphere is good because the free part of the group A. So the case n plus 1, we consider now a group, finite abelian group, and the order is 2 mod 4. And then we can show that Gn plus 1 of this Moore space is 0. Gn plus 1 of the Moore space is also 0 if we add the free part in the group. I mean, if we take at least 2 copies of Z and take the direct sum, we still have the Gottlieb group 0. And again, the rank 1 is delicate. What can we say if the rank is 1? So in this case, we have the inclusion because the previous argument, we can include this group in the image of Gottlieb group of the sphere because this is the free part. And we know that this group could be Z2 or 0 depending of any. So the idea now is to decide if this group Gn plus 1 is 0 or is equal to the whole Z2 group. To do this, it is enough to compute this white-hat product in red here. So we take the generator of the Gn plus 1 of the sphere, and then we compute white-hat product with the other inclusion, J2. Because with J1, we see that is 0 because of this fact. Yeah? So now let's try to compute this white-hat product in red. So we use inequality, and we have a formula to express this white-hat product in terms of this basic product composed with this element plus some other terms. These other terms, they are computed using iterated white-hat product. But what is the idea here? The idea is to show that this element on the left is non-zero. But since we use the James Hilton theorem, we are working with the composition of a homotopy group of the wedge in terms of each piece. So it's enough to us to show that at least one term is non-zero. And then we can concentrate in this term right in here. Also, we use this relation because here in the first formula, we have the identity of the Moore space is meshed with eta. And if we take the first element, or I mean n equal 2, we have this following relation using this smash product. And we was informed by this relation by Mukai. So we can use his computations to show that this element is non-zero. So what are these maps appearing here? We have inclusion of the sphere in the Moore space, and then the pinching map, because a Moore space can be obtained attaching a cell to a sphere using degree 2 map. So we have inclusion of the sphere in the Moore space and the pinching map collapsing to another sphere. And also this eta bar and eta tilde, it is common in this subject. They are extension and co-extension of these two maps. So if we take suspensions, we can show that this element on the left is iterated suspension in this Mukai element here. And then we have this formula on the right, and this element is non-zero. So with this, we conclude that this white-hat product is non-zero. And because of this, the generator J1 eta n does not belong to the Gottlieb set, the Gottlieb subgroup. So we started here with this generator of the Gottlieb group of this sphere, and then we were able to show that it doesn't belong to the Gottlieb Gn plus 1. So there are only two possibilities. So in this case, we conclude that this Gottlieb group is 0. But observe here, we use Z plus Z2. So now the general case, we use this fact. We decompose the group A as direct sum of the primary decomposition. Here we take the first decomposition for P1 equal 2. So we have the two primary components, and then we have the others for all the primes. Using this fact, we again decompose the Moore space, now using Z plus A as a wedge, and then we included this Jn plus 1 in the image of the first inclusion, using the component A2, plus the image in the other components. But now we know by the book from Golozinski and Mukai, we know that this part for odd components, they are 0. So Gn plus 1 of these Moore spaces here are 0 for prime greater than 2. So we simplify the formula, and then we have only the inclusion in the first part, using the first inclusion. And since the two component of the group A is Z2. And in this case now, it's important to use the order of the group. It is 2 mod 4. So this is why A2 is isomorphic to Z2. So in this case, we have this isomorphism here. And by the previous computation, we know that this group is 0. So this is the idea. We compute for Z2, and then we take the composition of the group A, and then we can extend the result. So the conclusion is this one. Starting from 3, if n is greater or equal to 3, the Gottlieb group Gn plus 1 of this Moore space is 0, but here, pay attention that the order of the group is 2 mod 4. So we can do the same techniques. I'm not going to show everything, it's similar, but we can go to higher groups. So I mean, we can take n plus 2, n plus 3, and so on. And then we have to use information from the Gottlieb groups of the spheres, again using the reference Golozinski-Mukai, and similar formulas for this kind of mesh product. To decide if the whitehead product is 0 or not, we need information about this mesh product. And then we have, for example, such situations. Gn plus 2 of this Moore space is 0. Observe here that we have 3 parts in the group. We have at least 2 copies of Z. If we have only 1 copy, if the rank is 1, this is also 0 if the order is 2 mod 4. But in this case, we can show that it is equal to the image of Gottlieb group of the sphere. So we have information about this group and they are equal. Okay, of course we have this kind of restrictions here. So what we have in progress, we are able also to compute replacing 2 mod 4 by 0 mod 4, because this is the only missing case to close the question. So for odd it is 0, and for even we are splitting in 2 or 0 mod 4. And this is what we almost finished, and we have this. So this is the main reference. I only put this for here. Paper from Arkovs Maruyama, from the book from Golozinski-Mukai, and these 2 papers from Gottlieb that I started. So thank you so much for the attention.
Okay, so let's thank the speaker for the talk.